why can I not just go from 0 to, what did I say this was, pi over 2? 0 to pi, right? And if I go from 0 to pi, well, something funny just happened. Anyone see what just didn't, or what just didn't happen? Let me do that again. All right? From 0 to pi over 2, I get the top half of that circle. But if I go from 0 to pi, I get the same circle. So what's happening? What's happening there? All right? Well, this is, the function is square root of cosine of theta. All right, so let's just draw a graph of that for a second. What I'm going to do is I'm going to draw a graph of the cosine. And now I'm going to draw a graph of the square root of that. Okay? So I have a point here, 1, and I have a point 0. But it's not the cosine, it's the square root. So it's going to be kind of a little smaller, right? And then what's going to happen between, I guess this is 2 pi, pi. What's going to happen between pi over 2 and pi?
Doesn't exist. It doesn't exist.
Doesn't exist. It's not defined. So if I integrate from here to here, say, it's kind of meaningless. It turns out, the integral will work, but there's something wrong there. So my choices are to either integrate from here to here, and then from here to here, right, where it is defined, or as I did in my example online, I integrate from here, negative pi over 2. If you do that, then you get a positive value. If you integrate from, say, from here to here, what happens? You get 0. So something funny is happening. Because this is well, the cosine isn't defined. The square root of the cosine isn't defined. But remember, we're doing this integration thing where we're taking little parts of the circle, and to get those, we're squaring the function and multiplying by 1/2. So it actually works out here, right? You square it. You're squaring a negative number. Well, take the square root of a negative number and you square it. Yeah, it's like we're doing complex integration. That's what we're doing. Ah, interesting. You can integrate in the complex plane, but that's way beyond this class. So, and you get a weird answer. I mean, what you get is positive area here and negative area and positive area that adds up to 0. That's how it's working. So again, these are take-home homework, think about them problems. They're not under the gun. Unless you've seen it before, they're not under the gun, figure it out kind of problems. All right, other questions on the homework? If I did, if you want me to go through the whole thing, I can. Anyone want me to go through to get the answer? It's really just about finding the right limits here. All right, we're ready to move on?
Sounds
Because I'm going to turn off the camera. All right. When last we left, we were discussing some kind of algebraic techniques to simplify integrals. And I left one out, and I'm going to go through it. It's not one you're going to see very often, but it can be useful to know this. Example, I think this is from the book, is we have 1 over square root of, in this case, minus x squared plus 8x plus 7. Now, this technique should work most of the time with something that looks like this, although the numbers may not be very nice. This problem has, even though it doesn't look like it yet, it has nice numbers. And we'll see that in just a second. If you look at the degree of this, it's sort of like 1 over, well, this is x squared, but it's the square root, so it's kind of 1 over, it's a degree minus 1 approximately. That doesn't mean we're going to be able to do it, but if you were concerned, like if there was an x up here, right, then it starts to look like a log, where, you know, the log of this, the derivative is 1 over this, and then you get the x on top. But again, this is kind of ugly looking. The trick here is something that hopefully you run into in early algebra, which is we want to take this and we want to make it into a perfect square. Does anyone remember what the technique is called to make that into a perfect square? It's not really a fancy term. It's called completing the square. So how do we do that? In the general case, you take ax squared plus bx plus c. And what do you want? You want b over 4a equal to c squared. That's how you do it. In other words, you want this to become a perfect square. Something times ux plus b squared. So we look at this, x squared plus 8x plus 7, and what do we want 7 to be? Well, if there's no a, if a is 1, you just take the b, divide it by 2, and square it. Right? So 8 divided by 2 squared is 16. So we really want this to be 16, so it's a perfect square. So how are we going to make it 16? We're going to add 9. Then we have to subtract 9, but since this is inside a minus, it's really plus 9. Right? Everyone see how I hand wave that? Right? Minus 9 plus 9 is 0. So we're good. Right? So let's rewrite this now. 1 over square root of 9 minus, now we have x squared plus 8x plus 16, which is a perfect square. So it's x plus 4 squared. And that's the form that completing the square puts us in. At this point, we have to do some substitution to get through this. So let's start off with the obvious u equals x plus 4. So du equals dx. So this becomes square root of 1 minus the square root of 9 minus u squared du. This still isn't quite where we want it, right? This is starting to look like what? Inverse cosine? Inverse sine? Inverse sine, inverse cosine. Okay, so let's do another substitution. Let's say v equals 3u. So dv equals 3 du, or du equals dv over 3. So now what happens? Okay, now we have 1 over the square root of 9 minus 9v squared times dv over 3. And now we're pretty close to where we want to be. Let's take this 1/3 out. And let's take 3 squared out from underneath here. So we have another 3. And now we have 1 minus u squared, v squared dv, or 1/9. And now this again this is the sine, inverse sine of v. So we have, everybody see if I'm writing down here? Yeah. 1/9 sine inverse v plus a constant. Now we have to backtrack a little, right? We have to plug in, v is now 3u, and u is x plus 4. So this becomes 1/9 the inverse sine of x plus 4 over 3 plus a constant. So that's a trick that could come up. Again, what you're looking for here is, it looks impossible because there's no x to go with the dx up here, but some kind of second degree under a square root that you can manipulate. All right. Any questions about this?
That should be 3 times x plus.
Did I do it backwards? V is 3u. Oh, 3u. Yeah. Thank you. Is that better? Okay. I'm not sure about that. Let's see what happened. What went? I'm going to leave it. Exercise for homework. See where I made my error. And, I did the technique right. I just didn't do the substitution right. Okay. That's the last of these kind of tricks. And now we are going to move on to a very important technique. It's kind of my favorite because it allows you to go in and figure out some integrals that are really weird looking at first, but it gives you a really great tool to deal with them. So before I get into this technique, I just want you to just take a look at a problem. Now we look at that and we go, wait a minute. I know how to find the integral of x to the n where n is not minus 1, right? And I know how to find the integral of 1 over x where it is. That becomes the log. But this integral, I mean, we don't really know how to go about that. I mean, we know it should be possible. I mean, this is more or less what this function looks like. So if I wanted to integrate from 1 to some value, there's some area under here, and I should be able to figure it out. I could do it numerically, but maybe there's a better way. All right. So before we learn how you do this, we're going to go back for a minute to Calculus 1A, and we're going to remember a formula that we used to use. What is the derivative of f of x times g of x? Okay. Well, you should know this like the back of your hand, right? It's going to be f of x times the derivative of g of x plus g of x times the derivative of f of x. Right. So we're going to take this formula and we're kind of going to reverse things a little here. What we're going to do is we're just going to integrate both sides. So on this side, we're finding the derivative with respect to, I just put in my x. We find the derivative, and then we integrate, and it's just going to undo itself, right? So we have f of x times g of x. And now on the other side, I'm going to write this in more sparse notation. I'm just going to say integral of f times g prime plus integral of g times f prime. And now I'm going to subtract this from both sides. And I'm going to switch things. So I get f times g prime equals what? Equals f times g minus integral of g times f prime. This is the formula you're going to, it's not too hard, we're going to go over it a few times, you're going to commit this to memory. This is the formula we use to do what's known as integration by parts. Now let me tell you what's so great about this formula. Right? You have some integral where the thing you're trying to integrate itself is a problem. But if we can instead translate this to its derivative, then the problem kind of goes away. So let me show you how this works in my simple example here. I do this in a very structured manner. I recommend you watch how I do it and repeat the way I do it every time, so that you'll kind of you'll be using the technique, but it'll be more on automatic. Right? So here's what I do. First, I identify what the two things are that are being multiplied here. And I call the one that I want to find the integral of f. So f equals 1. And the one I want to find the derivative of...
It should be on the opposite.
Yeah. Excuse me. And the one I want to find the integral of, I call that g prime equals, in this case, 1. So then I do my simple differentiation and integration. All right, f prime equals, well, what's the derivative of the log of x? Everyone should know that's 1 over x. And what's the antiderivative of 1? That's just x, right? So I always want to put it this way, line these up, right? Now, I set this equal to f times g. That's this times this. So it's x log of x minus integral of the bottom row. This is too easy. This is 1x over 1 over x times x dx. All right? So I get x log of x minus integral of 1 is just x plus a constant. Now, that seems so simple that I can't really just leave it. I have to check this, right? My mind just says, how did that work? This is the antiderivative of log of x. All right. Okay, so let's find the derivative of this. These two are multiplied, so I have to use the product rule. So x times the derivative of log of x, 1 over x, plus log of x times the derivative of x, that's 1, minus the derivative of x, which is 1. The derivative of c is 0. So this is 1 minus 1. I'm just left with log of x. Oh my, it worked out. Especially when you first start doing these, it's probably a good idea to check. Okay, questions so far? All right. Now we're going to try something a little more challenging. Just to get a feel for how this works. Let's look at integral of x e to the x dx. We really don't have any idea what the antiderivative of this looks like. I mean, how does this x get over here? If this was x squared, that would be different, right? Derivative of e to the x squared would be e to the x squared times the derivative of x squared, 2x, yeah. But this doesn't look anything like that. So what we want to get rid of here is this x. So let's set f equals x and g prime equals e to the x. And I'm going to use this same structure here. Now I'm going to write f prime equals 1. It's going to get rid of it. G prime, invert antiderivative of g prime of e to the x, just e to the x. And now I just plug into my formula. Again, I use this kind of diagonal here to tell me what's on the left. X e to the x minus integral of what's on the bottom. E to the x dx. So this is, of course, x e to the x minus e to the x plus c. All right, let's look at this just a little closer here. I have a product. It's two things multiplied together. And I'd be happier if I, instead of integrating this, I can integrate the derivative of this times the antiderivative of this. That's what makes this simple. Okay. Another example. That will be similar to this one. I want to find the integral of x sine x dx. Again, you should always check, but this is not sine squared of x. That would be easy, right? we just do a substitution for x squared, and this would be part of the du. But we don't have that. And again, we want to get rid of this x. So f equals x, g prime equals sine of x, f prime equals 1, g equals, okay, what's the antiderivative of the sine of x? It's the negative cosine of x. Again, I look down the diagonal here, x times minus cosine of x, negative x, cosine of x, minus the integral of what's on the bottom, minus cosine of x, well, 2 minuses. We're back to x. All right. So this is negative x cosine of x plus sine of x.
Professor,
Yes.
can you write out just like a template type, like the formula of it on the board so I can figure this out? If you know what I'm saying. Not with any example involved. So I'll just write that.
Okay. I don't know if this is going to
Oh, it was
satisfy you, but I'm going to say, let's integrate f of x times g prime of x dx. Maybe you want me to do this. All right. No, this is actually the way to write it. This is equal to f of x, g of x, minus f prime of x, g of x, dx. This is the formula. Is that what you're looking for?
Yeah, that's perfect. Thank you.
And again, if you think about this, if you just find the if you find the derivative of both sides of this, what do you get back? You get back the product rule. That's where it came from. Before we do the next one, I'm just going to, I think it's worth noting here that when we use substitution, what are we using? We're really using the chain rule. And now where we use integration by parts, we're really using the product rule. I feel like I want to fill in more, here, well, okay, we have the quotient rule, what can we use that? I don't know.
Yeah, right.
We're not there yet. Just something to keep in mind. Right.
What section is it? 117. Why don't you say 7?
Here's an example with this over here. Here's an example with just a rational function that's a little bit annoying to deal with. So before we attack this, let's take a look at the fact that the derivative of 1 over 1 plus x squared squared, write this a little more carefully, is what? Well, it's this to the negative 2, so the power rule tells me it's going to be 1 plus x squared to the minus 3, or 3 here, times the derivative of what's inside, times, of course, negative 2, times using the chain rule, what's in here, 2x. So this is negative 4x over plus x squared cubed. So this gives me an idea of something I might want to find the antiderivative of. Right? So let's try and break this up then into negative 4.
2 beta. How did it become 1 4?
1. You do this the right way. This is going to be my g prime, right? Negative 4x for 1 plus x squared cubed. Right? Times negative x squared over 4 dx. Let's see what I just did. This is a little tricky. I'm kind of thinking backwards. I'm saying, here's something that I can get to, right, by finding the antiderivative of this. So this is going to be my g. This is going to be my g prime, and then this will be my g. And then I just, take whatever's left. So f equals negative x squared over 4, and g prime equals negative 4x over 1 plus x squared cubed. F prime is going to be what? Negative x over 2. And I already figured out my g. That's just 1 over 1 plus x squared squared. I'm going to erase my intermediate steps so I can go from here. Okay, so again, look down the diagonal. That's what's on the left. Negative x to the 4th over 4 times 1 over 1 plus x squared squared minus the integral of what's across the bottom here. Okay, negative x over 2 times 1 plus x squared squared. And I'm going to get rid of my minus 3's and put my 1 hand out in front. Okay, now this looks more doable, right? This is 1 plus x squared squared. So I can substitute, right? You can say u equals 1 plus x squared. Du equals 2x dx, or dxx equals du over 2. Right? So I've got x dx over here. So this becomes plus this half, and this half becomes 1/4. 1 plus x squared. So it was to the minus 2, so it becomes to the minus 1. Right? Divided by minus 1, so it becomes a minus again. This is done here, right? This is just negative x. Is that right?
Why would you multiply by 1
Why
half?
did I say x to the 4th here? I mean x squared. X squared over 4 times 1 over 1 plus x squared squared.
Yeah, it shouldn't just become 1 because you're already multiplying by 1 half. You pull out the 2.
Plus c. Don't forget that. All right. Again, this is a little trickier, but kind of see how it makes it possible. This didn't look okay because the derivative of this, that we're going to get when we use the chain rule is just 2x. And here we've got x cubed up front. So by doing this manipulation here, we've now made it possible to integrate, instead of the thing that we didn't want to integrate, the thing we did want to integrate, which is this guy. All right. I think I just have one more example here. No, two more examples. The next one will show you how we can use this to our advantage when we have an inverse trig function involved.
Yeah, no, I got it. I got it.
This is a great technique. It just makes all these weird integrals doable. All right. We're going to do this one as a definite integral. We're going to go from 0 to 1. So the inverse tangent of x. Question? So we look at this and we have no idea how to integrate the inverse tangent. But we do know how to find its derivative, right? So we're going to set f equal to the inverse tangent. And g, well, there's nothing else there, so g is 1. G prime, thank you. Getting the idea. Good. So f prime is 1 over 1 plus x squared. And g is just plain old x. So again, look down the diagonal. X inverse tangent of x. Now I don't have to integrate this. It just sits there, right? Minus integral of x times 1 over 1 plus x squared. X over plus x squared. You can kind of do this one in your head, right? Put 1/2 here and 2 here. Now this is 1 over, this is of the form, use some other letter, h prime of x over h of x. Right? This is a form we see a lot, and this of course is log of the absolute value of x, right? So this just becomes, let me write the whole thing out. X tan inverse of x minus 1/2 log of absolute value of 1 plus x squared plus, oh, we're not going to add c here. Now we're going to have a definite integral. Okay, why did we want to do that? I don't know. Inverse tangent of 1. Pi over 4. So 1 times pi over 4, minus 1/2 the log of 2. Don't need an absolute value. Minus, okay, inverse tangent of 0. They're both 0. 0 minus log of 1, 0, right? So this kind of goes away. So it's just pi over 4 minus 1/2 the log of 2, or if you like, pi over 4 minus the log of square root of 2. That's pretty nice. You can imagine that you're going to be able to pull this trick with other inverse functions. Okay, the last example looks like all the other examples until you try it. And then something funny happens, and it works out anyway. It works out a little different. All right. So we're going to look at x squared Well, we did something like this already, right? So it looks like f should be equal to x squared, and g should be equal to, g prime should be e to the x, f prime is 2x, g is e to the x. So this equals, again, going down the diagonal, x squared e to the x minus the integral across 2x e to the x. Let's take that 2 out. That didn't really fix it, did it? But wait a minute, we've done this before. All right, we'll do it again. Integral of x e to the x dx. My new f is x. My new g prime is e to the x. F prime is 1. G is e to the x. So this becomes x e to the x minus integral of e to the x, or x e to the x minus e to the x. But that's what goes here, right? X squared e to the x minus 2. So sometimes you have to do it, the integration trick, integration by parts trick twice. Now imagine what happens if I make this 3. Anyone want to guess, hazard a guess what's going to happen? It's going to get worse, right? You're going to have to do it 3 times. Okay. Fun with integrals. What time is it? It's time for a break. Let's take a break, and then we'll come back. We'll work on some of these problems. We'll try some of them, and we'll go from there. Okay? I'm going to pass this out now anyway. Let's get started. Break time, right? Break?
Yes. And my new doesn't text me. I'm gonna be honest with you. Like, it's worth 5% of it.
How did that sneak in there? Well, I guess maybe some evil teacher wanted to torture you. That's all I can think of. I'm also going to suggest, even if we go over some of these, that you do them yourself as part of practice. I mean, I'd be happy to post answers too, if that's what it comes to. All right. Is anyone not through 1 and 2? That doesn't mean you finished it, it just means you beat your head against it. Does everyone beat their head against 1 and 2 a little bit? I'm going to take silence as a yes. Because that's all I ever hear. One says integral from 0 to 1 x squared of 1 plus x dx. So I want an f and a g. I might add, in some calculus books, they just like to use u and v. That's fine too. I prefer that. Someone want to give me just a guess? Doesn't have to be right. A guess as to how to break this up.
F is x, and then g prime is square root of 1 plus x.
Okay. That looks like a smart idea, because once we find the derivative here, it kind of goes away, right? All right. Go away. Now, this all kind of depends on, can we find the antiderivative of this, which is 1 plus x to the 1/2. So this will be 1 plus x to the 3/2 divided by 3/2, which is this. I'm glad we're doing this because I didn't really do specifically a one of these. There are two ways you can deal with limits on a definite integral for this kind of problem. I'll show you the alternate method, an obvious one. But anyway, so this becomes 2x 1 plus x to 3 over 2. And now we can evaluate this at its limits, 0 and 1. We didn't change the variables, so they're the same limits. And now minus this integral, which is 2/3 1 plus x to the 3/2. This isn't too hard either, right? This is just 1 plus x to the 3 to the 5/2. Now divided by 5/2. Again, from 0 to 1. All right, so now we have to start evaluating this. Oh, that goes away. That's nice. 1 times 2 to the 3/2 minus 0. That's 0. So this is just 2 to the 3/2, or if you like, square root of 8. And then what do we have here? This is now, put all these constants together, 4/15.
Oh yeah.
2 to the 5/2 minus,
Professor,
yeah.
why is the up at the top? Why is it where you cancel 2 over 2? Why isn't it? I think it should supposed to be 2 over 3 instead of 2 over 2.
Oh,
Yeah.
thank you.
Yep.
You can't cancel. Okay, so 2/3. Okay.
And also, I think the limits of integration are 0 to 3, not 0 to 1. But I don't think it really matters at this point.
Oh,
Yeah, it's 0 to 3.
oh goodness.
Yeah.
Well, that makes a lot of difference. Start over.
What's important is the method.
Okay, so this is now 4. The square root of 4 is 2. Cubed is 8. 2 times 8 is 16. Oh, and this 3 and this 3 are going to, they're going to cancel. Right here, minus 2/3. Okay, 3 square root of 3, square root of 4 is 2. 2 to the 5th is 32. And 264. 228. 128 over 15 minus, and then 0. So that's going to be 1 to the 2/5, so minus 4/15. Minus 2/3 times 24/15, or 16 minus 2/48 over 45. Oh, I think there's a snowball's chance in hell that I didn't make an error on that. But yes.
Regarding when you plug in the numbers like 0 and 3 into the equation, can you just
You mean here or here?
Both times. When
Yeah.
you do it, can you? Is it possible that you wait till like you get the whole integral
Yeah.
and then you plug in the
Yeah, you
numbers?
can do that.
Okay.
I just wanted to show that as soon as you get this part, which you didn't really integrate, you just multiply these two things together, you can evaluate these here and here.
Okay.
I didn't leave those up.
Okay.
Yes, it might be simpler to simplify it in algebra,
Yeah.
right?
Yeah. Okay, cool.
Good point.
Yes.
Okay. You know, I'm looking at this and I'm wondering, I don't think number 2 is, I think I made a mistake here somewhere. These don't seem like the problems I wanted to be giving you. All right, we'll just give it a try. This just looks like a substitution problem. Oh, goodness. You know, I'm very sorry. I seem to have given you the wrong worksheet. That's what it looks like to me.
It says integration by parts.
Yeah.
I'm supposed to have the
Yeah, this was, I'm really sorry. I did not give you the right problems. Okay, well, I'm sure the homework problems are right. There actually was one more example I wanted to show you, too. And I think it's my favorite example. Yeah, this doesn't look right at all. This one probably is, but I'm gonna just. Nobody said anything either. Guys, just speak up when the professor makes an error. All right. I want to show you one more problem because I think the result is really surprising. I want to find the integral or the antiderivative of e to the x sine of x dx. This is one of the most surprising results from just, boring finding antiderivatives. So, all right, let's take a look at this. What do we obviously want to do? We want to make f equals the sine of x and g prime e to the x. So f prime is the cosine of x and g equals e to the x. So this becomes e to the x sine of x minus e to the x cosine of x. Now we look at that and we think, that didn't help at all. I mean, I start with e to the x sine of the x, and I end up, and I have e to the x cosine of x. That's not any better.
Can you do it again?
But I don't give up, right? I'm going to do it again. I'm going to go over here, and I'm going to say, all right, e to the x cosine of x dx. All right, f equals cosine of x, g prime. Insanity is doing the same thing continuously and expecting something different to happen. So we're really out there into insane world here, right? Yes. All right, f prime is now negative sine of x, g equals e to the x. So this becomes e to the x cosine of x minus, well, there are two minuses, so it's plus sine e to the x sine of x. seems really demoralizing, doesn't it? I'm back where I started from. I've got that same annoying integral.
You can substitute.
Oh, don't give it away so quickly. Let them enjoy the irony. But I'm going to plug this in, right? Right? Let me erase this. So I have e to the x sine of x dx equals e to the x sine of x minus, well, that thing, all right? Let's plug it in carefully. E to the x cosine of x plus the integral of e to the x
Sine.
sine of x
dx.
dx. And let me distribute the minus signs, minus. Okay. Well, these two are the same, so let's get them on the same side, right? Add this to both sides, right? So I have 2 e to the x sine of x dx equals e to the x sine of x minus, well, might as well take that out, right? Wait a minute. If I divide by 2, I magically have my answer there. There's a moral here. If you use integration by parts, you end up back where you started from. That might be okay. That might be the answer. Now, fortunately, this came out to be a minus, and this was plus. What happens if this comes out to be plus?
That's 0.
And you've gotten nowhere, right? You haven't gotten anywhere. But fortunately, in this case, it did. All right, yay. All right, I'm just gonna leave it. We're really leaving early today, but we're gonna spend some time on the homework. I hope you will. Yeah, it's not really due till next Thursday. Please do some of the homework problems because you're going to need to practice this. You're going to learn how to do it, and I want to go over it next week. We'll go over it also on Thursday if you still have questions. But please come in prepared to do some of these. And as always, I'll hang around here if you have other questions. You want to harangue me about it?
Yeah, except I would, so that would take way too long.